Now we proceed to another type of capacitor, which is cylindrical capacitor. Cylindrical capacitor consists of two coaxial cylindrical conductor of different radii, one of its being grounded. Here we only discuss when the outer cylinder is grounded. Let us take a cylinder of radius A. Let us take a cylinder of radius A and place a charge Q on its axis. Then what happens? Then this Q charge will be uniformly distributed over these cylindrical surfaces, right? And we consider this cylinder is of very small radius. That means we have considered that A is very small. Now this Q charge, right? Q charge is given to this conductor. And if length of the cylinder is L, then length of the cylinder is L, then charge per unit length, that means on the axis, if we axis taken as the this, then charge per unit length is Q by L. L is the length. Now we place another cylinder of radius B with the same axis. Then a conducting cylinder of radius B is placed concentrically with the cylinder of radius A, and the outer cylinder is grounded. Then what happens? Then we know that outer cylinder will be charged by the process of induction. That means there will be induced charge on the inner side of the cylinder, and that will be minus Q, and plus Q charge will be induced on the outer surface of the outer cylinder, and this plus Q charge will be neutralized by the charge of earth. Now what happens? Now the field lines are starting from inner cylinder, terminate on the outer cylinder. Why terminate on the outer cylinder? Because it is grounded. Field lines will start from the inner cylinder and terminate on the outer cylinder, because outer cylinder is grounded. Now the charge Q is spread on the axis of the cylinder uniformly, and the charge per unit length is lambda equals to Q by A. Therefore, field in the space between the two cylinders at a distance, let us say R, will be equal to, field strength will be equal to lambda R hat divided by 2 pi epsilon naught R. We have calculated that using the Gauss's law. How we calculate that? Field in that space between the two cylinders is given by E equals to lambda R hat divided by 2 pi epsilon naught R. Therefore, the potential difference between these two cylinders will be equal to V is equal to integration minus E dot dr. That means minus integration, and the radius of the outer sphere is B. B is greater than A, will be equal to lambda R hat divided by 2 pi epsilon naught R dot dr. That means integration lambda dr divided by 2 pi epsilon naught r. This will be the potential difference, and we get this as lambda is constant, which is q by L by 2 pi epsilon naught integration dr by r is equal to from b to a, or we can say minus 2 pi by epsilon naught log r. Integration of dr by r is log r, and r is equal to from this. Now 2 pi epsilon naught, this is log a minus log b, or we may write lambda by 2 pi epsilon naught, this is log b minus log a. We bring this minus sign to inside the bracket, or lambda equals to q by L twice pi epsilon naught L log b by a. That the capacitance of the cylindrical capacitor is equal to C equals to q by v, and q divided by 2 pi epsilon naught L log b by a, or 2 pi epsilon naught L divided by log b by a. Q cancels out, and capacitance per unit length, that is capacitance of the cylindrical capacitor per unit length, is equal to capacitance per unit length. This capacitance per unit length will be equal to 2 pi epsilon naught divided by log b by a. C by L, that is L cancels out, or we get C0, which is the capacitance of a cylindrical conductor per unit length is equal to 2 pi epsilon naught log b by a. We made here an assumption that this cylindrical capacitor has infinite length, right? Because if the cylindrical capacitor is not infinite, then in this region field will not be radial, right? We make this assumption to this calculation.